graph. That's probably not gonna be as obvious on that one. Brandon, you got a guess on that one?
Like 1 to the x.
How about if we just made the negative, flip the thing over? Then it's gonna do something like this,
Right.
but then it's gonna be too low. So we need to add something to it. So if we did on that, now a t equal to 0, e to the 0 we said is what?
1.
1. 1 minus 1 is 0. It's that boundary condition. Okay, at t equal to infinity, what was e to the minus infinity? That was 0, so we end up with 1, but what do we want to end up with? We end up with 10. So equation on that, scale factor is 10, so it's going to be 10 volts, 1 minus e to the minus 2 over RC.
And that 10 volts, that's just given.
It's because whatever the, actually, it's whatever this battery is the value, because that'd be the value at an infinite time. Just like this is going to be the battery divided by the resistance V over R. We get e to the minus t over RC. Nathan, what are the units on that exponent?
Ohms.
Ohms? Probably not. Dan Floyd? No, it's Brock Hamlin. What do you think it would be?
CEEN current per time, or something per time.
We have to evaluate something like, let's go the other way. 4 to the power of 2 ohms. What's that going to evaluate to? Doesn't make sense, does it?
It's a constant.
Your exponent can't have dimensions. This has to be an integer, it has to be a real value. So this has to be dimensionless. You can't have ohms, you can't have amps, it's got to be dimensionless. It just has to be a number. Given that, Josh, what are the units of the numerator?
Seconds.
It's going to be seconds. Therefore, what are the units of the denominator have to be?
Second.
Has to be seconds also. So if you were to multiply R times C, you're going to come up with units of seconds on that. It's going to be time. And if you were to do the definition of what an R is, volts divided by amps, and what the units of all this is, do a dimensional analysis, you'll find that R times C does give you units of time. So this RC is going to be called the time constant of the circuit. This units of time is constant because we've got physical components that aren't changing values. And quite often the time constant is shown with the Greek letter tau. Connor, yes, right there. What's the time constant of this circuit, or how would I compute it?
take the 1K
Okay?
and multiply that to the,
Which is gonna be the 1 microfarad, what's
Yeah.
micro? 10 to what? 10
To the
negative
negative 6.
Some people, last class said 10 to the minus 3. 10 to the minus 3 is milli. So micro is this. So what's that evaluate to?
10 to the negative
instead
3.
of -3.
Which is
Milli.
1 millisecond. So our time constant on this circuit is 1 millisecond.
So that means it takes 1 millisecond for the voltage to, on the capacitor equals 0, or 10 volts.
No. In a couple minutes though, we'll figure out how it is gonna work on it. But the time constant does dictate how fast or how slow all this stuff is gonna be happening. Okay. Given all of that, now I'm going to put some numbers in and calculate voltages and currents on this. I want to evaluate this at the current at 1 millisecond. So the current is going to be 10 milliamps, e to the minus 1 millisecond, divided by R times C. And we said that's also 1 millisecond. So milliseconds cancel, so I get e to the minus 1. And the calculator display isn't working reliably, so this is going to be ending up to be 3.68 milliamps. Okay. And something that's usually confusing in the book and the first time we're going through it, the author is going to ask to evaluate this at time equal to 1 time constant. Well, t at 1 millisecond is equal to 1 times the tau time constant. And when we plugged all that in, this was e to the minus t over RC. So if your time is equal to 1 tau, time constants cancel and you have to e to the minus 1. So that's usually a real confusion factor on the problems in this section. Okay, next what I want to do is get the voltage at that same time. And it's going to be same exponent, e to the minus 1. And when we crank through that, .32. So after 1 time constant, I'm at 6.32 volts, the final is going to be 10, so I'm 63% of the way to the final value. And on this, decreased to 36.8 of the original value. Next, let's do it for 2 milliseconds. Which is 2 time constants. So plugging that in. T 2 tau divided by the denominator time constant tau, plus we have just e to the minus 2. .35 milliamps. And my voltage. So I'm up to 86.5% of the way. Rather than do all of these, let's jump to t equal to 5 milliseconds, 5 time constants. So we're getting close. Derek Jensen, how long is this going to take until I reach the 10 volts and the 0?
Would you have to go to infinity?
What was that?
Would you have to go, I don't know,
I think you were right. What did you say?
would you go to infinity?
It's going to take an infinite amount of time. We're never going to reach that. We're going to keep getting closer and closer and closer. But we don't reach that. But we're sort of impatient. We can't wait forever. So we got to figure out what's close enough. And industry standard is if you waited 5 time constants, you've waited long enough. So 5 time constants is a rule of thumb for being fully charged. And note that rather than being at 10 volts, we're at 9.93. We're 99.3% of the way there. And anything beyond that, you know, you've lost it in the accuracy of your components anyway. So rule of thumb is 5 time constants. Just say, oh, capacitor's going to be at 10 volts, current's going to be 0. Okay. Next time, we're going to be having a quiz over mesh and nodal analysis, and then we're also going to be taking a look at coming up with equations when we're doing the discharge part in addition to the charging part.
So